For 100 years, we thought we knew exactly how our world would end. We were told that the Milky Way was on a dead-set collision course with Andromeda, a massive inevitable crash that would rewrite the stars. It was a scientific certainty, but that certainty just vanished. The galaxy collision, the one scientists can't explain, has already started. But it is not the disaster we were promised. New data from the Gaia spacecraft has sent shockwaves through the halls of NASA. The head-on collision we have spent decades fearing, the math just changed. The probability has plummeted from a sure thing to a staggering, chaotic flip of a coin. But while experts argue over the new numbers, something else was discovered. Deep in the dark between the stars, the two galaxies have already touched. The invasion has begun, but not in the way anyone expected. If our survival is not guaranteed anymore, then what exactly is heading toward us in the dark? In 2012, the future of our galaxy seemed written in stone. The Hubble Space Telescope team, led by Roland van der Marel, delivered what felt like a cosmic verdict. The Milky Way and Andromeda were on a direct, unavoidable collision course. The numbers were chilling in their clarity. The Hubble Space Telescope's proper motion measurements, just a handful of micro-arc seconds per year, translated into a transverse velocity for Andromeda of only 17 kilometers per second. That was barely a sideways drift, set against a head-on approach of over 100 kilometers per second straight toward us. The verdict from the Monte Carlo simulations was almost absolute: 95% probability of a head-on collision, timed to erupt in 4 to 5 billion years. The two galaxies, each with a mass of about 1.2 trillion suns, locked onto a radial track by gravity's invisible hand. For the better part of a decade, this was the story written into textbooks and whispered through planetarium domes. The Hubble data gave us a universe that felt precise, almost comforting in its fatalism. We could imagine the Milky Way and Andromeda as two solid islands, fated to merge into a single, giant elliptical Milkomeda, while our sun drifted to the outskirts, a passenger on a predictable journey. The error bars were narrow, the probabilities unyielding. Even the uncertainties, tucked away in the appendices, seemed like polite footnotes to an inevitable disaster. There is something almost nostalgic about that era, when the cosmos seemed to obey the rules we wrote for it, when the only unknowns were how the final fireworks would look, not whether the crash would happen at all. We lived inside that certainty, breathing in the numbers as if they were air. But the universe is not a machine. It is a vast, shifting ocean of dark matter and invisible forces, a cosmic pinball table where the rules can change overnight. The Hubble team's 2012 forecast was not wrong. It was simply the best that could be done with the tools at hand. They built a model of fate out of 3 deep Hubble Space Telescope fields, a handful of background galaxies, and a proper motion error of plus or minus 30 kilometers per second. For a moment, it was enough. Then Gaia Data Release 3 arrived, and the illusion of certainty began to unravel. Gaia Data Release 3 did not arrive quietly. It struck the field like a silent detonation, scattering the old certainties in every direction. The numbers themselves were unambiguous. Where Hubble's verdict had given us a gentle sideways drift, just 17 kilometers per second, Gaia's measurements shattered that calm with a transverse velocity of 166 kilometers per second, an order of magnitude higher than expected. The impact was not just in the speed, but in the mathematics that followed. For the first time, the full covariance matrices, those hidden webs of uncertainty binding position, distance, and motion, were laid bare for the Milky Way and Andromeda system. The error bars, once polite and narrow, now sprawled across the chart like cracks in glass. When these correlations were fed into the orbital simulations, the clean, sharp peak of collision probability dissolved into a broad, chaotic spectrum. Timing estimates that once clustered around 4 billion years now spread from 2 to over 9 billion years. The probability of a direct, head-on collision collapsed from near certainty to a coin flip, sometimes as low as 20%, sometimes as high as 70%, depending on the assumed mass and concentration of the dark halos. In the most rigorous studies, the outcome became bimodal, a chance for an early, violent encounter or a long, slow gravitational dance that might never end in merger at all. The illusion of fate, so carefully constructed by the Hubble era, had been undone not by a single new measurement, but by the realization that the universe's variables are entangled in ways we had not respected. Each tiny shift in a star's position, each subtle bias in the Gaia astrometric frame, rippled outward through the equations, amplifying uncertainty until the future of our galaxy was no longer a script, but a probability cloud. We are left, not with the comfort of a scheduled apocalypse, but with the knowledge that our cosmic future is tangled in the invisible hand of covariance, where the fate of the Milky Way and Andromeda is balanced on the edge of statistical chaos. The numbers no longer offer assurance. They only urge us to look for evidence in the silent gaseous atmospheres that already fill the void between the stars. Project AMIGA began with a question that cuts through the fog of theory. If the Milky Way and Andromeda are truly on a collision course, can we see the first touch? Not in the blinding light of stars, but in the ultraviolet shadows cast by their invisible atmospheres. Over 6 years, AMIGA's team assembled a grid of 38 ultraviolet sightlines, each a flashlight aimed through the void, each a silent witness to what lies between. The Hubble Space Telescope's cosmic origin spectrograph, tuned to the faintest whispers of OVI, CI, and CSI, delivered the numbers, column densities in the range of 1 to 3 times 10 to the 14th per square centimeter, traced not once or twice, but again and again across the sky. These are not random coincidences. AMIGA's brightest quasar targets, probing within 75 kiloparsecs of Andromeda's core, show absorption profiles that match the predicted velocities of M31's own halo gas, velocities plunging past -200 kilometers per second, metallicities that betray their origin in a galaxy, not a lonely cloud. The further out the sightlines reach, past 140, 200, even 300 kiloparsecs, the signatures persist, stitched together from HST, FUSE, and ground-based spectra. Each detection is a fingerprint, a chemical handshake in the dark. The numbers add up to more than just a catalog. Monte Carlo simulations run by the AMIGA observers show that the odds of so many velocity matches appearing by chance are less than 5%. The implication is clear. The gaseous halos of the Milky Way and Andromeda are no longer separated. They interpenetrate, forming a bridge of ionized gas that stretches for hundreds of thousands of light years. We are not waiting for a collision. We are already breathing the air of another galaxy. The evidence is not without controversy. Some argue these signals could be the debris of the Magellanic Stream or the remnants of ancient outflows. But the metallicity ratios, silicon-2 to silicon-3 and oxygen-6 to carbon-4, point to a richer, more massive origin. The AMIGA catalog lists these values for each of the 38 sightlines, a forensic map of the invisible. In the cold logic of absorption columns and Doppler shifts, the old illusion of isolation dissolves. The first contact has already happened. The only question left is how far the bridge extends and what it means for the fate of both galaxies. The illusion of separation dissolves when we trace the true boundaries of our galaxies. Project AMIGA's ultraviolet sightlines cut through the darkness, searching for evidence not in the blaze of stars, but in the metallic fingerprints of gas. The numbers are quietly astonishing. Along quasar TXS 0400 plus 123, 85 kiloparsecs from Andromeda's heart, a Psi-3 absorption feature appears at -210 kilometers per second. Its metallicity, roughly 0.3 times the solar value, betrays an origin in a galaxy's enriched outskirts, not a stray high-velocity cloud. This is not an isolated case. 5 stellar sightlines, cross-matched against AMIGA's quasar grid, reveal the same velocity signatures, the same chemical ratios. Each detection is a chemical handshake, a confirmation that the Milky Way and Andromeda are already sharing their atmospheres. The bridge is not just theoretical. Neutral hydrogen surveys, mapping the 21-centimeter line, show the HI envelopes of both galaxies reaching out, their edges intersecting at a distance of about 120 kiloparsecs. Here, the density of gas rises above 10 to the 18th atoms per square centimeter, forming a filamentary corridor that aligns with the future collision axis. This is not the pristine emptiness once imagined. It is a fog of shared atoms, a zone where the distinction between galaxies blurs. Monte Carlo simulations run by the AMIGA team assign less than 5% chance that so many matched velocities could be coincidence. The metallicity, consistently higher than in the Magellanic Stream or typical galactic high-velocity clouds, speaks to a massive ancient origin. These are not the remnants of tidal debris or local outflows. They are the breath of two galaxies mingling in the void. The numbers have weight. The HI edge, the metallicity ratios, the persistent absorption features all converge on a single, unsettling conclusion. The gaseous halos of the Milky Way and Andromeda are no longer separate. They interpenetrate, forming a shared, turbulent atmosphere that stretches for hundreds of thousands of light years. We are not waiting for a collision. We are already inside the event, breathing the mixed air of another world. The next chapter will not be written in the calm of isolation, but in the chaos of overlapping atmospheres, where every new perturbation, every passing satellite, every ripple of dark matter can tip the balance of fate. The Large Magellanic Cloud is no passive bystander. With a mass of 150 billion solar masses, nearly a tenth the heft of the Milky Way, it drags a gravitational wake behind it, distorting the very center of our galaxy. For decades, the LMC was treated as a minor satellite, a curiosity of the southern sky. Gaia data release. 3 changed that calculus. The numbers are stark. The LMEC's gravitational pull is strong enough to shift the Milky Way's center of mass by thousands of light years and to torque the galaxy's dark halo into a lopsided shape. This is not a subtle effect. The LMC acts as a cosmic lever, tilting the entire local group's gravitational balance. Simulations that factor in the LMC's mass reveal a new twist in the fate of the Milky Way and Andromeda system. The merger, once forecast for 4 billion years from now, is delayed by at least 800 million years of cosmic reprieve, bought by the LMC's invisible hand. The mechanism is pure orbital mechanics. As the LMC plunges through the Milky Way's dark matter halo, it transfers angular momentum, shifting the Milky Way's trajectory and subtly altering the approach vector toward Andromeda. The effect is not linear. It ripples through the equations, amplifying small uncertainties into a broad spectrum of possible futures. Tilsawala's 2025 suite of cosmological simulations, seeded with Gaia Data Release 3's phase space data, ran thousands of alternate histories for the local group. In nearly every realization that included a live LMC, the time to first contact stretched beyond the Hubble era's predictions. The odds of a direct, head-on crash drop, while the probability of a long, drawn-out gravitational dance rises. The LMC's torque is not just a footnote, it is a pivot, turning the collision from a scripted event into a cosmic improvisation. We are left with a universe where even the largest predictions can be overturned by a single satellite's mass. The LMC, once dismissed as a minor actor, now holds the power to delay the fate of 2 galaxies. The comfort of a scheduled apocalypse dissolves, replaced by a new kind of suspense. The knowledge that our future is being rewritten by the silent drift of a companion galaxy hidden in the dark. Triangulum, or M33, lingers at the edge of the local group's unfolding drama, a spiral galaxy with 50 billion suns orbiting Andromeda at 200 kiloparsecs. For years, its influence was overlooked, but Gaia's latest data has forced a reckoning. Triangulum's gravitational pull, once a minor footnote, now shapes the fate of 3 galaxies. Its tangled orbit with Andromeda injects a new volatility, shifting what once seemed a straightforward merger into a far more unpredictable encounter. Simulations seeded with Gaia's phase space data reveal the pericenter, the closest approach between the Milky Way and Andromeda, no longer sits at a fixed point. Instead, It sprawls across a plus or minus 45 kiloparsec range, a margin wide enough to decide whether galaxies graze or collide head-on. Triangulum's gravity can tighten Andromeda's spiral, drawing the collision axis inward, or just as easily fling it outward, making a near miss more likely. Each scenario is a roll of the cosmic dice, with Triangulum as the unpredictable hand. But the chaos does not end with galactic orbits. When three massive galaxies interact, the rules of orbital mechanics turn ruthless. The three-body slingshot, once a theoretical footnote, now stands at the center. During close encounters, stars can be hurled away at escape velocities, transformed into hypervelocity scouts racing into intergalactic darkness at over 1.5 million miles per hour. These are not rare flukes. Monte Carlo simulations predict tens of thousands of stars ejected in a single pass, their paths scattered across the void. The Sun itself is just one of millions caught in this gravitational crossfire, its future uncertain. Triangulum's presence broadens the spectrum of possible outcomes. The question is no longer just when or if the Milky Way and Andromeda will merge, but how many stars will be lost to the void, how many will become wanderers. Each simulation with M33 in play amplifies the unpredictability, turning the future into a cosmic lottery. 12%. That is the number we inherit from Til Sawala's 2025 simulation suite, a number that transforms cosmic chaos into human risk. In a universe where the fate of galaxies is no longer written in stone, 1 in 8 suns like ours will be cast out, exiled by the gravitational crossfire of giants. Not a gentle drift, but a slingshot through the void, at speeds reaching 670 kilometers per second, fast enough to leave the Milky Way behind forever. Fast enough to become a hypervelocity scout, a solitary ember hurled into the dark. This is not the fate reserved for the unlucky few. In Sawala's ensemble, the ejection of stars is a statistical certainty, a consequence of three-body encounters and the invisible hand of the Large Magellanic Cloud. Each simulation is a new roll of the cosmic dice, each outcome a reminder that the Sun is not immune. The odds are precise, 12%. The velocity, unthinkable, 1.5 million miles per hour, enough to cross the gulf between galaxies in a single human lifetime. We are forced to reckon with a future where the Sun itself may become a refugee, stripped from its home, wandering the silent corridors between galaxies. The numbers do not offer comfort, they offer only the truth. The universe is not obliged to keep us close. The next chapter is not about who collides, but about who escapes, and how far they must travel through the dark. Far beyond familiar stars, a hidden force draws the Milky Way and Andromeda through space. This is the Great Attractor, a massive unseen presence near the Norma cluster that pulls our entire supercluster, Laniakea, at over 600 kilometers per second. Its influence is traced not by light, but by the way thousands of galaxies, including our own, are swept along in its gravitational current. Less than 5% of this mass shines as stars or gas. More than 95% is dark matter, invisible except for the way it bends the paths of galaxies. The true scale of our uncertainty lies here. The fate of our galaxy is shaped not only by local orbits or mapped bridges of gas, but by vast unseen concentrations of mass that do not emit or absorb light. Every simulation and prediction rests on this invisible foundation. The universe reminds us that the greatest forces shaping our future are hidden in darkness. Tonight, we stand inside the overlap, breathing Andromeda's gases, blind to the 95% of dark matter guiding our fates. Gaia data. Release 3, Project AMIGA, and the coming Sawala analysis reveal a universe ruled by chaos, not symmetry. The invisible hand has never felt colder. The next move belongs to the dark. In the end, we are all refugees in a cosmic pinball game with no promised path home. What would you do knowing that?